going to hear me say type safe a lot during this talk because I still haven't gotten used to the name change myself. It just came out last week. So that's probably my boss calling to say, don't do that. But what I thought about for this talk was that I would do the talk that I'm scheduled to give, but try and give it as quickly as possible as far as not go deep into looking at code and stuff like that. And that way at the end, we could have a Q&A session and talk about Lightbend and the future of Scala and what this new logom thing is that we're talking about now. Unfortunately, you know, we haven't even released logom yet, so it's not like I can do much of a presentation about it yet. But does that sound good? Is that something you want to do and just have a Q&A session and talk about all these weird things that are happening? Yes? No? Yes? All right. Well, then let's do it. Awesome. So I have been a Scala developer for almost 7 years now. Oh my goodness. And almost all of that time I've been doing actor-based development. So I wrote a book called Effective Akka. It was about all the things that I stumbled over whenever I was trying to do this. But then the head of the Akka team, Roland Kuhn, and I started working on a book called Reactive Design Patterns. And when we were working on this book, the first thing we realized was there's all these different concurrency models out there. And we really wanted to focus on explaining what they were and where they have relevance. Because a lot of times, I think, as a community, we get hung up on saying something stinks. And that may not necessarily be true. It's more that this thing is being used in the wrong way. So yes, I'm from Lightbend. Yes, I love Akka. But it's very easy to misuse Akka. You use it in the right places, and it has, you know, real value. So we wanted to talk about all these things, and we wrote a chapter called Tools of the Trade. And it was all about the various tools that we have, at least today, for how we can write concurrent code. So businesses in general, they absolutely have to change right now, right? They have inputs coming in from all of these places that they didn't 5-10 years ago. And that means that they've got to have systems that can stay up and run and work and scale to be able to handle all this additional load. And I know most of you, how many people have not seen the Reactive Manifesto? Okay, great, that's awesome. So I don't have to explain it, right? But the thing about the Reactive Manifesto and the ideals that we're pushing with the Reactive Manifesto is that there are actually costs. When you think in terms of Amdahl's law, you have to structure your applications to minimize the amount of coordination and the amount of ordering that needs to take place when you're dealing with data coming through. And if you don't, you pay a tremendous cost. So for example, if I have a 100% parallelizable system where there is no coordination, I don't care what order things come in, I don't care that they are handled, like I have to wait for something else to happen. If I have that, then I can scale linearly, and that's fantastic. If, on the other hand, I have any of those properties where I'm not commutative and I have this dependency, well, even 1% drop in your parallelizable code means a 60% drop in your efficiency. It's a mathematical fact based on Amdahl's law. And worse yet, it actually does not stay in this, you know, speed up realm where it maxes out. It actually starts to go down. And we see this with tools like, you know, Cassandra, with tools like Akka Cluster. The more nodes you're adding, the more overhead that has to take place where these nodes are making sure that they're all up and doing the things they're supposed to be doing. So instead of handling data, they're doing coordination, right? So that's the universal scalability law. And those are costs that we have to take into account when we're building systems that are going to be elastic and resilient. When it comes to resilience, the critical thing about this is you have to have supervision. And if you don't have supervision, something else watching the work that is being done, then you don't have resilience. You basically have something like system D, a daemon on the computer that is going to restart the process. And that's not resilience, that's just restarting. So we need to have something always watching over the workers that we have, right? There's validation failures. We don't worry about those from a resilience standpoint. That's somebody entering a phone number with a letter by accident. You can design your API to say that's not right, or maybe even the UI so that nobody could ever do that. But you need a supervisor always watching the processes that are going to do the work as a result of that. Now, the costs of not being reactive are very tangible to your business, right? There's the cost of the wallet, because you're using more machines to do your work when you don't need to. A really classic example of this, anybody ever hear of a company called rapgenius.com? Okay. Well, they were annotating rap songs so that people would understand what rappers were talking about, and therefore, providing meaning and context to rap songs. But they pivoted to annotating the web, right? And that meant that suddenly their base was much larger. And at the same time they were doing this, they were running on Heroku, and they were using Ruby on Rails. And even if they were using Passenger or Unicorn, there was a physical limit to the amount of work that every one of these dynos on Heroku could do based upon, the threading model in Ruby. Well, whenever Heroku changed their routing to not be round robin, 1, 1, 1, 1, 1, but instead be random, 1, 1, 1, 1, 1, they complained and said, you know what? That hurts us because we could spin up more servers, but we don't actually know if they'll be used. Their real problem was the way they designed their system, not the way Heroku's routing strategy had affected them. But that was the symptoms they saw. The effect was, that they thought that they were, not being able to scale more. And the critical thing about this was to handle just 10,000 or 11,000 concurrent connections, they had to run 300 dynos. That's a real cost to a startup on the order of $30,000 a month. Well, in the JVM world, we kind of laugh about that and say, I could run one server and do most of that work and maybe a second just for some, redundancy. So, a real cost to you as a business, but I mean, let's think about it. We're wasting electricity. We're wasting all these machines doing stuff that they could be doing better. And, if you're not reactive, you don't have the ability to deal with failure when one of those Rails servers goes down. That's a problem because now you're not being responsive to your users. Now, functional programming is key. I am a Scala developer, and I was a Java developer who had to teach himself how to figure, how to write functional code. And when I say functional programming, I don't necessarily mean things like category theory and all those fancy words that are so, they're daunting as a developer. I just mean the idea that you're going to write code which can be applied to data containers anywhere they live. So, for example, look at Java 8. When we were running Java 7 and we were writing our iterative loops and doing work that was imperative, right? We'd have to create a collection that was going to be where we put the data. Then we'd iterate through the collection where we had the data. We'd do a transformation and put the data into that collection. You see this with the Hadoop API. It's really difficult to spread that work across multiple boxes. However, if you have a function and you have a representation of data, then you can apply the function independently of the location where it's going to run. So functional programming is really critical. This is why Java 8 implemented lambdas. It wasn't to kill Scala. It was because the programming model of the future requires the application of functions to data, whether that data is in a future, in an RDD in Spark, whether it's in a collection or an optional, what have you, right? But the great thing about this, it also has some real benefits. Things like it makes your code more declarative. You're not writing all of that, how to do the work. You're merely focused on what you want to accomplish, the transformation you want to take place. If you can do that, then you're in great shape. So I am a functional programming fan, but then again, there are times whenever I'm writing code, especially on the JVM, where I have to drop out of it for performance reasons and write something imperative because the JVM only understands imperative code. It has no idea how to optimize functions per se, right? It's not a functional platform. So we run into these issues a lot as developers, whether we're using Java 8 or Clojure or Scala or whatever on the JVM. So backpressure is a really important part of this. Up until now, a lot of people have been thinking in terms of, I'm going to put a circuit breaker in front of my code. And if I'm overloaded and I'm not able to handle all the requests that are coming in, I'm just going to shut down. Where I'm going to open the circuit breaker so that nobody can send me requests while I handle this stuff. But you were totally making a guess about how long that window should be. 250 milliseconds? 100 milliseconds? I don't know. It was a guess. But if we have backpressure, we don't have to worry about that. And you see that now with things like reactive streams. We'll talk about that a little more shortly. So I'm going to talk about these various technologies now. And all of the code is available on github.com in the reactive design patterns repository. So you don't have to make sure you capture this. You can go download it, run it locally, play with it all you want, whatever you want to do. This particular code is in the chapter 2 section. So first thing, event loops. How many people have used either Node.js or Vertex? Okay, that's a fair number. I'd say on the order of 20% of the room. So when you're writing something in an event loop, just think in terms of a wheel. If you have various processes, things that you want to do, it's adding them to this wheel of work, right? And that's great because when it reaches a point where it can say, you know what, I've either got a fairness model or I've got, you know, something that's going to allow me to do other work while this work was doing something like, you know, maybe asking a database for a response. What it can do is, you know, say, all right, I'm going to move to the next thing in the wheel, move to the next thing in the wheel, move to the next thing in the wheel. But there is also a little bit of a problem with that, particularly with JavaScript. JavaScript is a language which is not terribly sound, right? And that means that it's very easy to forget to write a test. And then a type error occurs on just one thing that you deployed that was running inside that event loop, and now it took down everything in the event loop, right? Now you could have try catch and try to catch the exceptions, but that's only the ones you know about. And so the ones you didn't, well, that's going to take down that process, and then you have to restart with systemd. Now, Vertex in version 3 was supposed to get a little bit more supervisor capability, and I'll be honest, I haven't had a chance to look at Vertex 3. But I do talk to Tim Fox, so I should ask him about it. The really critical thing about this, though, is making sure that you're doing more than just try catch, right? You have to have something there watching over all of the threads in Vertex or the processes in Node.js. So, and you know, we always talk about this. Everybody says that in Node you have this concept of callback hell, if you pardon my language. I don't think that's fair to JavaScript or Node, because in a lot of respects, people are forgetting of all the callbacks we're writing in Java and Scala as well, right? Just because you pattern match something in Scala doesn't mean it wasn't a callback. So let's be fair about the models here, and also JavaScript now has promises, so you don't have to write these, you know, all callback style code. Now, a simple Node.js example here would be just to have a counter to show a value for every time a request came in. And you can see here I've just got a counter set to 0, and I create a server here using this HTTP library. I increment the counter, I write out, you know, a 200 response, and I want to show this text here with sending a response of the counter value. And then I start up the server. I've defined the behavior I want, and I start up the server saying what port to listen on and what host. And then, you know, I log out that it's up and running. Go ahead and start hitting me. The funny thing about this actually was, anybody ever try doing something like this in Chrome? No? Okay. Believe it or not, Chrome does this like double pump of your requests. So every time I was doing this, first one would be 1, then it'd be 3, then it'd be 5, then it'd be 7. I'm like, wait, whoa, why is that happening? Try it in Firefox, everything's fine. So, you know, you learn little things playing around with stuff like that. But Node is a really simple way to set up a server, and it's also extremely performant. You see tremendous numbers of people who are writing Rails backends who are saying, you know, I'm going to put Node in front of it just so that I can handle all the things that are coming at me and then scale up the backends to do the work behind it. It's expensive to do that, but it's still better than having Rails sitting right there at the front end. One of the really cool things that we've seen in the last couple years is that communicating sequential processes have become much more prevalent, right? This is the model that we see in closures, core.async. We see it in Go with the Go channels. Go has 2 parts to the language that are centered around concurrent running. One is Go routines, right? You define some behavior and you tell it to go off and run, sort of like a runnable in Java. But then the channels are much more about producer and consumer. I'm going to put something into the channel, and somebody is going to consume it on the backside. And then you have to start thinking about things such as, single producer, multiple consumer, multiple producer, single consumer. But that's up to you as a developer how you're going to implement that. And it's a great, powerful model for leveraging the cores on your box and spreading work across all of those cores. The flip side is it's limited to that box. There is tremendous research from way back when Tony Hoare was doing the original Communicating Sequential Processes paper about being able to distribute all of this work and also determine deadlocks, but nobody's been able to really implement it in the large yet. So this is an area where both Go and Clojure are going to grow, hopefully, over time, because that will allow them to abstract over the location of where the channel consumer has to be, instead of being local on that box. And also, there's still not supervision, but that's a mixed bag. In Clojure, you actually have a little bit better way to handle errors than you do in Go. How many people are Go programmers? Wow, okay. How many people have heard about Go's mess of error handling? You have to check and see whether the error was equal to nil, after everything that you do. It's horrible. But, it's effective. It's like a blunt tool that, you just check. Did it fail? Did it fail? Did it fail? Did it fail? And here is an example of some Go code. This is just going to put, 10 values into a channel, and something on the other side is going to consume them. And the 10 values are just going to be the value of I. I'm an old C++ developer, so whenever I see my for I equal 1, and then you do a nested loop, you have to use J. I've never known where that came from. Does anybody know why we use I and J for these things? But nonetheless, all we're doing here is we have one loop who's sitting there and producing values, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, putting them into the channel. And we have the consumer on the other side pulling them out of the channel and printing that information out. It's actually really simple to get started, and it's a great way to leverage all of the cores on your box quickly, right? But Go, whenever it comes to error handling, not so great, and you don't have supervision of the channel. You can't tell whether the consumer was able to handle that message successfully unless they are somehow messaging back to you. And if you're doing that sort of model, you definitely don't want to be using the same channel. You want to have a channel on the back side providing you with that information. Now, futures. How many people have coded in futures? Yeah. How many people have coded in Java 8 completable future? Yeah, this is the new hotness, because the old Java 7 futures were blocking. The API was only get, which would hold the thread until that value came back. I mean, the thread wouldn't be running on a core, but that thread is a valuable resource in the JVM. Every thread is a cost of roughly 512 kilobytes in size. So there's a finite limit to the number of threads you have available to your application. You can toy with that by setting some of the settings in the JVM, but that's a really, really low-level thing to be messing with, and can have unexpected consequences when you try to play with things like stack sizes. Anybody ever do this stuff? I'm not good at it. Somebody's like, yeah. I know. I've been there. But the great thing about futures is now that we have completable future in Java 8, we have the ability to say, go do work. And the thread doesn't have to be held onto, right? When we don't have to do that get, which just sits there until the value comes back. Instead, the thread can be used by somebody else. And that means now we have much more efficient usage of the threads inside of our JVM. Now, futures don't have supervision, but they do have the ability to tell when something failed on that future. So we look at the way we write runnables and callables in Java. Say we have a thread pool out there, right? And it's got, 10 threads available to it. Or, we're using fork join, and it's based upon the number of cores available to the JVM. When we're I lost my train of thought actually, trying to explain that. Let me get back to that. So this is an example where I am doing a typical, I've got a web request coming in, and I don't want to go to the database necessarily only if I don't find it in the cache. I want to do both at the same time. I want to go out and check the cache at the same time I'm checking the database. Yes, I'm using more resources to do that, but I'm lowering the latency of the response because it's not sequential, right? I'm doing this in parallel, and therefore I'm making sure that the response comes back, worst case, from whichever one first, right? And I'm using completable future almost in a promise kind of way, where I'm saying return the value of whether the cache future or the DB future finished first. Whichever one came back, that's what I want to send back and put into the response I'm giving to my user. So it's a much cleaner way to write code for futures than before. And with the callable and runnable, think about this. This is the point I was trying to make. What do you do on a callable and runnable when that thread fails? Has an exception, something you didn't catch. Where does it go? It goes to the console. Who's watching console in production? Oh, I'm sorry. No, I am. That's hard, right? You have to sit there, and anything that scrolls past, you just missed. You have to go get lunch. You have to watch the console while you're getting lunch. It's no fun. So instead, we have logs and stuff like that, right? And you have one tool inside of your thread pools that will allow you to capture this information. You've got your uncaught exception handler. Now, if you use that and you think, all right, well, what are all the things that could go wrong on this thread pool? Suddenly you're thinking, oh, well, a lot of things could go wrong in this thread pool. You have this massive try-catch inside of your uncaught exception, not try-catch, but handler for all the different types of exceptions that could have occurred. And that's no good because the code ends up being like this, and you still miss a whole bunch of use cases. So what does everybody do? They say, well, if it's just an ordinary exception, I'm going to log it. And at least you captured that instead of it going to the console, right? You have it in a log file, and you can do some later on digging into what went wrong. With futures, we don't have to do that. We can define callback behavior for what to do when a failure occurs. And we can keep that local here. It doesn't have to blow all the way up to the top of the thread stack. And the really great thing is, in the case of using a thread pool the way I just mentioned, the only effective way to do it is actually turn your thread pools into a domain concept, where I'm only going to perform customer updates on this thread pool so that I can define an effective uncaught exception handler for this behavior here that could go wrong. And that's no way to live. That's hard. So the whole idea of data flow is, this is really easy to get confused with communicating sequential processes. This is more continuations. The idea that I can define a set of behavior and then do other sets of behaviors. Anybody ever code in this sort of style? Yeah, you know what? It's going to become a lot more prevalent in the big data world. And you'll see this in Spark, right? There are Spark data flow libraries coming out of Google. It's interesting to see Google using Spark this way. TensorFlow is another thing coming from Google. But the idea of data flow is just you being able to say, I want to do this, and then do this, and then do that, and stage behavior in chunks, right? So these continuation models are another way of organizing concurrent code. In the Scala world, we have a library called async. Anybody ever hear of this? Yeah, not many. Okay, one person, two, three. Yay. It's not really well known, but this was a library that, we didn't sit around and say, boy, we want to create a data flow library in Scala. That'd be great. No, a large bank paid for this. As a matter of fact, the same large bank that paid for Slick. They asked for these things to be built because they came from the .NET world, and they really wanted to have these tools that they were so familiar with. And as a result, we have them now in the community. This was actually Morgan Stanley. Anybody see the video they put out just a couple days ago about how much they love Scala? It was great to see. Warmed my heart. But yeah, so we built this async library, and it's all about building these CPS-style continuations and data flows. And it's a really cool way to write code. Now, the platform really matters. How many people have heard of Quasar? Quasar is a tool. Okay, one person. Quasar is a tool out of I forgot the name of the company, but they have a really, really solid tech team, and what they're trying to accomplish is green threads on the JVM, and what they're doing is basically bytecode rewriting to make what is happening on your threads more efficient. Now, if you look at a tool like Akka, you look at a tool like async, Scala async, there's going to be a lot of context switching going on because it's going to do something on a thread. Whenever it's done, somebody else has to get on there, and that means that all of the data coming down to the core that is executing that thread has to be loaded up. And that can be a little bit painful of a process as far as time goes. We're willing to accept these because we get a lot more efficient use of code across all of the cores on our box. But what if we wanted to go a level deeper? What if we wanted to have continuation style programming here where we write green threads into the JVM? And that's what Quasar is trying to accomplish. It's neat. So it's this idea of fibers as well as another term for it. And it will mean less context switching because these are all wrapped into a thread. And that means they can be optimized by the cores of execution as far as prefetching data down so that it's ready at the time code is actually being executed. Now, I didn't have an example for that. Sorry about that. How many people have heard of RxJava? This came from the reactive extensions that were in the also in the .NET world. This really shows some of the incredible foresight that the Microsoft .NET world had about reactive extensions, about Link and the library for doing functional application of data returned from databases. They really have some neat stuff there. And reactive extensions are just the idea that we're going to take away what was the observer pattern from I'm old and I was a programmer in the 90s, and I had the book Gang of Four Design Patterns. Anybody else have this book? It was basically every interview you had to go through. If you just knew that book, you could get through any interview. Well, the ideas in there were actually coalesced, where they took the iterator pattern and the observer pattern. The iterator pattern is finite. You know that you only have 10 things in something, and you're iterating over it, right? Does it have more? Does it have more? Does it have more? It doesn't, I'm done. The observer pattern is where I subscribe to listen for an event, and that's infinite, theoretically. I could subscribe forever. And what reactive extensions did was combine the iterator and the observer into what we call the observable, right? And treat them the exact same way. So the code is actually fairly simple. To make it look useful, I actually have to have a test that's going to do something and allow somebody to subscribe and be notified of events. But I just set up to observe and subscribe, and now when things happen, I'm receiving these as events. Now this is really well known from the Netflix world, right? Ben Christensen and his team at Netflix were working on this for a very long time. The great thing about the way Netflix leveraged this is it doesn't mean that everything at Netflix is written using RxJava. No, they actually use a fair amount of Akka as well. The new Atlas tool at Netflix is largely Akka clustering and stuff. So in this case here, you see a very simple programming model for dealing with events that are occurring inside of your code. And when you have this kind of model, now you can start thinking in terms of streaming data, right? And that's where we see the Reactive Streams initiative coming from. I didn't mention it here on this slide, but this is where Lightbend in conjunction with Pivotal, companies that you would think are our competitors. The team from Vertex, Twitter was involved. Netflix was obviously involved with their RxJava implementation. We all sat down to define how are we going to deal now, knowing that this is the correct model for dealing with streams. How are we going to deal with the fact that streams can be overwhelming? Spark streaming had a really critical problem up until Spark 1.5, where if the data being processed took longer than the amount of data coming at it, you would lead to an out-of-memory error. And that's no fun in big distributed systems like Spark. So the idea of backpressure has to be implemented so that somebody can withstand the onslaught and communicate all the way back to the front end, whatever it is, wherever it is, that, hey, I'm working on it, right? So in these reactive streams implementations, There are varying implementations, like RxJava does it differently than Akka does. But there's always an asynchronous channel that is working in the background to communicate back from the consumer over to the producer. Here's the data coming at the consumer. Here's the consumer telling it how much more I can take. And as it's getting overwhelmed, it's slowly going down to, I can't handle anymore. That value is 0. And at the producer, asynchronously, when it realizes there's 0 there, it stops sending data until it's offered the chance to take more. When that value starts creeping back up, it starts sending more. And you can actually send this all the way back to TCP, all the way back to your clients, because TCP has backpressure in it as well. So, actors, and I think I'm pretty much on track right now. Good. How many people have coded in actors? Okay. And I'm also going to do the effective Akka talk later, which will be a much more, intermediate to advanced level discussion about actors. But the thing about actors for me is that they're very easily abused. Actors are technology that belong at the boundary of your system. And when I say the boundary, that could be cross-thread, that could be cross-JVM, that could be cross-box, right? Those are the places where Akka shines. It's really good at helping you build a resilient system. What you do on thread should not be actors, right? When an actor receives a message and now you have a process of work you need to do, you want to write that in as correct a way as possible. Actors are untyped, both in Erlang and in Akka. And believe me, we stole every great idea the Erlang people had because they had really good ones. But we had a statically typed language, whereas Erlang is dynamically typed, and everybody says to us, you call yourselves type safe. Ha ha ha. These actor interactions are totally untyped. And we're like, well, yeah. But are you typed whenever you work with RabbitMQ? Do you have types in that world? No. You could put anything into RabbitMQ. You try to define these through protocols using things like maybe, message formats and stuff like that. But still, there's no guarantees of correctness through any message queue that is, especially when they're distributed. And that is the fundamental crux of Akka. It gives you the flexibility to write code that stands out across cores, across boxes. Awesome. But it's untyped. And that means that you send a message, you have no idea whether the producer and consumer have a contract that is something the consumer is actually going to do. So it's very easy to make mistakes, right? There is a project out there called Akka Typed, and it's very nascent, very new. I don't know anybody using it in production, that's for sure. But it is our attempt to find a way to prove correctness statically in the message flow. The problem still comes in time. When you think about time, if I'm an actor, I can change my behavior. Somebody sends me a start message. I only listen for the start message. But when that comes in, now I switch to handling only these other messages. And I don't listen for start, right? But then I get maybe an end or something like that, and I switch back to only listening for start. Because of that variability in what messages I can handle at any point in time, I can statically check that my actor will handle this message, but I can't prove that it will handle it at the time it's received. That's a pretty critical thing as far as correctness goes. So think about these things when you're leveraging Akka. You want to use it because you want to spread work across cores and give up that location focus of saying everything has to operate sequentially here. Instead, I'm going to send messages to various workers who can just do this work on multiple cores. And you know what? It fans out across boxes, and it doesn't change your code at all. That's great. The other really important thing is you have supervision. Everything that is happening, even if it's off thread, even if it's on another box, is supervised. You always know that this failed, and you get a message as a result of that. So that's pretty exciting, and it gives us a lot of new tools for writing code. Now we can think in terms of failure, just like we do all the successful cases we have. We're really good at saying that we want to model our successful cases, like updating customer information, all the things that go right. We're so bad about writing code to deal with things that are wrong, and that's a whole domain itself. It is. Anybody here do domain-driven design? No, some. It's a great way to define the context inside of your application, and domain events aren't just the things that go right. They're also the things that go wrong. So in Akka, I don't want to sit here and show like a whole Akka application. I just want to show off that I could have an Akka actor that is doing supervision of another actor. That other actor is going to pull stuff out of some queue. Maybe it's in Kafka or something like that. And it's holding JSON. And it's going to parse that JSON and put it into a class that represents a customer or something like that. And then it's going to put it in the database. And you can say, yes, that's a really poor single responsibility principle implementation because it's doing multiple things. But bear with me. If I have a case where I am parsing the JSON and the JSON is bad for whatever reason, like my phone number that has a letter in it, well, I can capture an exception that is invalid JSON, and that just means that okay, I want to put this thing that failed off to the side to be handled later on, but keep going, resume right there, right? So I save the JSON that failed, and then I resume my actor, go get more JSON and keep trying. But then what about the times when I can't connect to the database, right? That's also a problem, but on a much bigger scale. And it's probably affecting a lot of different actors at the same time. I can actually say, are all of you failing in this way? I mean, it means I have to do message passing to figure that stuff out, but I can make assertions about what's happening in my system and then tell C3PO or whatever I'm using, BoneCP, to retry these connections and give me new ones, and I won't do anything until I get them, right? So it allows you to define domains of failure, and that's super exciting. So regardless of whatever tools you're choosing, think in terms of the trade-offs that are involved with each one, because it's not that people are inventing concurrency models to confuse anybody. It's that they solve certain problems, and each one of them is useful in that regard. So when I hear somebody say that I'm only going to use, a certain language or a certain tool or something like that because, it has this one thing that I could just use everywhere, that's not how we want to think about writing good code. It's not how we want to think about writing systems that are going to, scale in the real world. Because you know what? It's very easy to misapply them. So that's it. Now we have time for questions. So does anybody have questions about Lightbend rebranding from TypeSafe? Questions about, how we're not going to be the Scala company anymore? Yes. Why? Okay. So the question is, why would we do this? Being named TypeSafe is a really great name to developers. It is. I love it. Right? It means something to me. The problem is that when we're talking in the enterprise, it means absolutely nothing. They don't care about type safety. And worse yet, it actually ascribes a property to our company that may not hold water in the future, right? We want type safety now. Who knows what the future holds? And so when you pick a name based upon a physical property or something like that, you're actually limiting your ability to serve different markets. And over time, we think that by choosing something utterly nonsensical, it gives us the freedom to not be bound by the preconceptions. There are other reasons as well. I mean, every time I tell somebody I'm from TypeSafe, in the enterprise, they say typeface. And I remember just in December, I was at a conference. We had a booth, and this was a big Gartner group thing, and there's all these managers walking around, and they just look at things and go, move on. Well, they come to TypeSafe. And a couple people would just look at it funny because they'd see this big diagram of big data and fast data architecture and all this really cool stuff, but they'd see TypeSafe. They'd just kind of wrinkle their eyebrows and walk away. And whenever they'd come back, if they came back, they'd say, "Oh, I thought you made fonts, or I thought you helped me type better." So, I mean, TypeSafe is a great name for those of us who know about it and care about this stuff, and it hurts me to let it go. I mean, it does. I really didn't want to. But I'll admit that this is a lot better than some of the other ideas people came up with. Did I explain the why? Here's another example. I was just thinking about this. Confluent is the company around Kafka. And Kafka is an amazing tool. It's becoming ubiquitous in the world for dealing with all these things coming in, striping out log-based event data. But what if confluence isn't a property of their systems in the future? Confluence meaning I've got 2 streams coming down to 1, right? What if that isn't the future for them? Then they're beholden to a name that, is not relevant anymore. You also saw this with Spring Source. What if Spring wasn't their core product? What if over time, Cloud Foundry is really their core product, but they were called Spring Source, right? People would have assumptions about them as a business, whereas as Pivotal, they can be anything and not have those. It's a great name, really. They can be anything, and there are no boundaries to them as a business because of their name. I know it's crazy to think that people think this heavily about names, but this is why people come up with nonsense names, so they're not bound to realities. Anybody else? Questions? Like the effect on Scala? Anybody worried about the impact on Scala? Why did we release Logom, this new microservices framework, Java first? There's a really practical reason for doing that, actually. Play framework was written by a consultancy in France, and it was called Zenexity at the time. Now they're called Zengularity. And we bought the rights to Play framework from them. Play 1 was purely Java. Play 2 was purely Scala. And when you think about it, the names were probably kind of poor, because then people expected that they could just go from Play 1 to Play 2, and you really couldn't. And trying to bolt Java APIs and functionality over Play has always been really hard for us. We are a company that believes so much in Scala, but when you have people who are saying, I've got to learn all this stuff about concurrency, parallelism, the cost of forking and joining all these jobs together, all this distributed programming stuff that we never had to think about before, do I also really want to learn a new language, right? A lot of them don't. And so we have a platform which works for both the Java and Scala world, but the Java world is still adapting to these ideas. And you know what? Scala developers tend to be more, I don't know, they embrace change a little more. They're not as afraid to pull in something that's a risk, right? And sometimes to their detriment, But that means that typically they've implemented a lot of the things that are going into Logom themselves over Play. Whereas Logom is going to be a RESTful API building microservice tool where we are going to tell people exactly how they should build it. For example, CQRS is the default in Logom. You are not going to be pushed to do CRUD. And by that I mean you're not going to have a database in place that's doing updates of data and reads of data at the same time. We're instead designing this entire system such that you are always writing stuff into a write store, transforming it so it can be read on the backside. Microservices are a terrible name. I tweeted about this the other day. I like to call them isolated services. The only way you can have real microservice architecture is if they don't share anything, right? Because if you introduce dependencies between microservices, you've just created a monolith anyway. You can't share a database, right? If you shared a database between 2 services, what do you do when one of them requires a schema change? You have to update both services. You can't do that. You can't share protocols or define. Ben Christensen did an amazing talk about this just the other day, where he was saying that if you're putting a client in front of anybody, you are now binding systems together instead of letting them be free-form between themselves. Right now, a lot of people, to create that isolation, are using HTTP REST, right? But there are other ways to do it as well without introducing a dependency between systems. So those are the critical things. And you can't even share code between services, right? The second you say, I'm going to create a core module or a commons in my company or anything called miscellaneous, forget it. Get rid of it. Throw that idea away. Because that is exactly something that somebody else is going to pull into another project. And now, when you go to upgrade, you've got to figure out how you're going to deal with this dependency between 2 different projects where one of them didn't need to change, right? You see this, Ben used the example of Guava. Anybody here using the Guava library from Google? Really handy library for writing better collection-based code. And there's a whole bunch of utilities in there for things like hash code and toString and equals. Well, what if you have to go to the next version of Guava? And you've got it across all of these different it's a dependency, shared dependency across all of these different projects. Your host. It could take months to figure that out just to update Guava. So don't, right? Have a dependency to Guava inside of one project, have a completely different dependency inside of another project, but don't share code such that they have the same dependency and now your host. Don't do that. So isolated services are what we want. Logom is going to be a framework that pushes people exactly in this direction, right? With default, so you don't have to make the decisions. And then when you want to make a decision to not follow the default behavior, you can override it. It's up to you. So that's the goal of Logom. And yes, I mean, this is us coming out swinging against Spring Boot. We think the idea of building microservices based upon the servlet model and CRUD databases is a poor model. But it's the standard that we know so well, right? It's difficult to say that these new ideas are definitely going to take off. I don't know. Is the idea of CQRS, where I have a write store and a read store, going to take off and everybody going to use it everywhere? I'm not sure. I'm not even sure it's valid in every use case, but still, we think it is the future of scalable services. So we're pushing in that direction. This is going to be, we think, a big difference for people. Yes, question? No? Oh, thank you.
Hello. A question about physical boundaries for actors. You said that actors should be put on the physical boundaries of your system, but not on the work on the thread.
Yeah.
So could you please elaborate on it a little more with example or something?
Yeah, sure. So I get a request to do work on, say, update a customer, right? So I get an update customer message from another actor. Now, the second I receive that, I have a whole bunch of steps I have to take. And what people sometimes try to do is parallelize it by creating other actors and sending that work off to them. Whereas I would much rather somebody did something with futures and use not necessarily composability is what I want. Composability of multiple interactions. Now, mind you, that's still crossing a physical boundary, but I'm localizing a context, right? So if I can define a context that represents something that may cross a physical boundary, but has a logical context together, then that's how I try to organize that code. If I'm writing anything that is CPU bound, if I'm going to write something that is going to go off and take 20 minutes to calculate pi to the millionth point, that's a terrible thing to put like just inside of an actor, because that actor is now unresponsive to the outside world. If you want to, you can do that, but you could also spawn work on another thread or do it all local to that actor right there and have all the safety checking and stuff like that, but not try to push stuff out to another actor where you're giving up that guarantee of knowing whether the message was handled, right? That's the key thing about it is, do I have to know whether this was handled? Then I can say, I want to keep this inside the actor on thread or something, or use futures. I think maybe by saying physical boundaries, I'm actually kind of making a bad point there, because futures are across a physical boundary, but what I want is composability. Does that make sense? No? Okay. So, yeah, let's talk about it outside, actually. Would that be okay?
Just to continue this question, there is such an idea in the Scala world that you must use actors whenever you have state or some kind of endpoint which is state of an external system, and for everything else you just use futures to have type safety and compatibility.
I'm not sure that that's some people do. Like, for example, if you follow Von Vernon's work, where he has his reactive messaging patterns in Akka book, he also wrote the book Implementing Domain-Driven Design. He's very much about building real-world views of your customer base, or the domain to your business using actors. That can be good, but I mean, in essence, you are creating a live cache with all of the penalties that come associated with managing a live cache of data. So I don't reach for that first. I tend to try and reach for going with a stateless model, and I pass state in messages, right? And I have worker actors that don't have state doing work. That's the first way I'd like to use actors in Akka, where I say, all right, well, an update customer happened, or a group of customers did a whole bunch of things with their Fitbit. I don't know. But I'm now routing those requests across to actors who are going to do some work, and then, you know, they are they aren't holding on to state themselves. They know what to do when they get a message, right? That's the easiest way to think in terms of Akka. If you go with state-based actors, then you have to do things like figure out how you deal with deletes, right? And deletes are always hard in any system. I like to, if I can, farm that kind of business out to data stores where they can have data sharded across multiple nodes so that we don't have overloading of one node and stuff, and they can do replication really well. You can do this with Akka. Akka even has a replication library now called Akka Distributed Data using CRDTs, conflict-free replicated data types that they're using in React. But that, you know, it's complexity. I want to avoid complexity. State means complexity to me, right? If I can keep state in messages and make my actors just be workers, it's a simpler model. Does that make sense? Okay, well, yeah, I mean, that's totally valid. I mean, this is just me, right? We all have very good opinions and reasons for thinking that, so, yeah. I guess time's up. All right, thank you.